Let's go with a quick review for what we have talked. So this should be the architecture 3 lecture. Now I didn't remake the lecture 5 and lecture 6. This should be lecture 7 actually. So I don't exactly remember the lecture number here, but I made one slide just for 2 lectures together. So last time we talked about the vector add example, right? Then how to write a kernel code. Now we were discussing how to run this kernel code in GPU. Then we talk about assembly, how a shifted copy works in an assembly. Then here's the key part. The most important part is there are several type of instructions. There are scalar instructions, vector instructions, global load, which is a vector memory instruction. Right, there are different type of instructions, and the swait here, swait count, is a scalar instruction that explicitly doing the synchronization. So there are a few different type of instructions. Now we haven't touched how these instructions are executed in a compute unit. So this is the goal of today's lecture. And let's quickly go through these slides. Now we talk about thread divergence, how we use an execution mask, a predicated execution model to support branches in a GPU kernel. So now we mainly talk about even if these threads are not taking effect, they still occupy resources, they still take time. Okay, so that's something that every programmer wants to avoid, but it's actually very hard to avoid. So just whenever it's possible, then we can avoid thread divergence. Now we start with GPU architecture. We start with CPU-GPU link. Then the GPU has a command processor. The command processor is a CPU within the GPU. It controls the whole GPU, all other resources, how other resources work in a GPU. Then we have direct memory access or DMA engine, which is responsible for copying data between the CPU and GPU. There are 2 of them so that bidirectional copy can happen at the same time. Then we also talk about asynchronous compute engine, which is supervising the kernel execution process in a GPU. Then there are multiple ACEs so that multiple kernels can run at the same time. Then we talk about compute unit. In AMD terminology, we call it compute unit. In NVIDIA terminology, we call it the streaming multiprocessor, SM or SMX. Those are GPU cores. It contains registers, that's where the instructions are executed. Then if we evaluate how powerful a GPU is, we evaluate how many compute units are there or how many SMs are there. NVIDIA SMs are slightly more powerful than AMD CUs, but AMD typically at the same range, same tier of the product, AMD has more compute units than SMs, NVIDIA SMs. So typically there's no, theoretically, there's no good or bad comparison between AMD GPUs and NVIDIA GPUs. If they're roughly the same tier, their computing power are similar. Sometimes AMD may have even higher computing power. Why NVIDIA is more commonly used today is mainly because of the CUDA system. It's the software and the ecosystem is just easier to program. And because NVIDIA started this trend earlier, so programmers usually have the habit of first to try NVIDIA GPUs first. Okay, so I would say even today, AMD ecosystem programming environment still has a distance compared to NVIDIA system. Okay, now we talk about compute units. What compute units execute? So compute units execute blocks. The ACE will divide the kernels into blocks and dispatch those blocks into the compute unit. Okay, so the unit of dispatching is always in a block. One block, all the threads within one block have to be executed in one CU. But one CU can execute multiple blocks at the same time. Then we talk about the resources constraints, say how we can determine how many blocks can execute on one CU. Then there are basically 4 different constraints. One is the number of wavefront slots. One is the number of scalar registers. There are scalar registers, as you see in the program. Then we also have vector registers, and also the shared memory, or sometimes in AMD terminology, is called local data share. Okay, these 4 type of resources that's limiting the number of blocks that can be dispatched in a CU. And definitely, we want to dispatch as many CUs as possible to the as many blocks to the CUs as possible, so that CUs will have more threads waiting there to be executed, right? So it'll have opportunities to select which compute unit can execute. So there's a common thing for compute architecture here. It's called latency hiding. So what is latency hiding? Latency hiding is there's sometimes you have some latency, right? So for example, one thread maybe, or one warp may be accessing memory. Accessing memory takes a very long time. It's several hundreds to thousands of cycles. So it takes a very long time to get the data back. But while we're waiting for the data to get back, we can do something else. The calculation unit or the combinational logic in the compute unit can try to do something else. So this is a process called latency hiding. So we have a long latency that is for memory access. We hide the latency by doing something useful. Then we don't feel the pain of the long latency of memory access. So for both CPUs and GPUs, we need to consider what's the mechanism for latency hiding. Okay, so if we have more blocks waiting there to be executed, we have more chances for latency hiding. Okay, then that's the dispatching process. Then we try to dispatch as many as possible. But this dispatching takes time, so dispatching process can be the global performance bottleneck sometimes. Then we try to, in earlier AMD GPUs, we try to write the kernel in 2 different ways. One is just one thread is executing one piece of data. The other way is just to have a relatively fixed number of threads. But each thread is responsible for a chunk of data. In that way, we can see 2 times speed up or 2.5 times speed up. When I say 2.5 times speed up, it's actually a lot of speed up. So if originally it takes 1 second to execute, right? The new execution will take about 0.4 seconds to execute. That's 2.5 times speed up. That's the longer time divided by the shorter time. That's a speed up. Okay, so I think last time we stopped here, right? So we want to talk about what happens in a compute unit. So this is how the instructions are executed. So let's start from here. Wavefront pools. Wavefront pools are where we say the wavefront slots exist. And it's very interesting that wavefront pools is not an AMD terminology. It's not an official AMD or NVIDIA terminology. It's made up by people while they're making simulators that they created this terminology. Then it's getting commonly used. So if you say wavefront pools, some people may know this term. Some people may not know this term. It's okay. So we describe wavefront pools as a list of wavefront slots. Now, for most common AMD configuration, there are 10 slots per pool. Okay, 10 slots per pool. That means there can be 10 warps that or 10 wavefronts resides in each wavefront pool. Okay, so in total there are 40 slots available there. So 40 warps can be executed at the same time. Then that comes the question, how many blocks can be executed there at the same time? Then you need to ask how many warps are there in the block, right? It depends on the program. It depends on the block size. So if your block size is 256, that means on AMD system, 64 thread is a block. 64 thread is a warp, right? So 256 threads means there are 4 warps per block. In that case, we can run 10 blocks in this CU at the same time. Okay, if there's only 1 warp per block, we can run 40 blocks in this CU at the same time. So it depends on the block size. The verbs from block can reside in different wavefront pools, and actually it's preferred to reside in different wavefront pools. Okay, then so we have wavefront pools, right? Each slot, what are there in each wavefront slot? It's basically registers that records the state of this wavefront execution. So for example, PC registers, the program counter points to the next instruction to be executed, PC counter. Program counter, then execution mask, other state registers, and also instruction buffers. So which is a group of registers that stores the instruction to be executed that is already fetched from the instruction memory. Okay, then we need to say, oh, what instructions we need to execute next. So where does instruction stores? Instructions are nothing special but data that's stored in the main memory, right? So instructions are stored in main memory. This is von Neumann architecture. But the core of von Neumann architecture is that instructions are part of the data that stores in the main memory. You fetch instructions from the main memory so that you know what you need to do next. Okay, so GPU is basically still von Neumann architecture. So there's a fetch unit that connects with the instruction memory, right? It connects with the instruction memory to fetch data for the verbs. And then the verbs, I'm just writing four wavefront slot in which each wavefront pool there. But just imagine there are 10 of them. Okay, so this fetch unit is mainly an arbiter. What is an arbiter? Arbiter is when multiple entities are competing for one resources. Then the arbiter needs to decide who can get the resources. Okay, question? Yes, so the instruction here is mainly L1 instruction cache. Okay. And the instruction cache is shared in a group of 4 compute units. So there's one cache per 4 compute unit. Okay, so next lecture, we're going to talk about the memory system. Today, we're going to focus on the instruction pipelines. So the fetch arbiter can decide which wavefront can fetch data. Okay, so there's no fixed algorithm for the fetch arbiter. There are many different ways that we can arbitrate, right? So for example, in one way, we may want the one wavefront or one verb to execute as soon as possible. Then that like whomever have been fetched most recently, then this arbiter may select that one. Or in another way, if we want all the wavefronts to execute have a similar progress, then we want the fetch arbiter to select the one that have not been fetched for the longest time. Okay, so we experimented this thing before, then we realized driver can control this policy. So there's no decided policy for each GPU. It can just change from time to time. Okay, then the fetch arbiter or the fetch unit can access the instruction memory, load the data, and store it in the instruction buffer of each wavefront slot. And in each wavefront slot, at this moment, we have instructions to be executed next, right? So what do? We need to decide who can execute, right? Then we have a issue arbiter. So what is an issue arbiter? Issue arbiter decides which instructions or which verb can send the instruction to be executed in the real unit that can perform that action. Now here, there's a terminology for core design that's split by the issue stage. Before the issue stage, we call it the front end. So basically where the instructions are loaded and the instructions are buffered. Then the rest, where the instructions are executed, is called the backend of the instruction pipeline. Okay, so it decides which instruction to execute and perform the arbitration process. We'll talk about this arbitration process soon. It's a little bit complex. So probably need a half an hour to talk about the arbitration process. But we need to understand what's the instruction pipeline, what units are there so that we can execute instructions. The instruction pipeline looks like this, or at least very briefly looks like this. So there are 5 instruction pipelines. Branch unit, which execute conditional branch or unconditional branch, so a jump instruction. A scalar unit will execute instructions start with an S. Right? A vector memory instruction will execute instruction starts with a global. VLU instruction will execute instruction start with a V. Then LDS instruction is for local data share. It controls a small part of memory here. Okay, it will execute instructions for that starts with DS. Okay, so data share. In theory, there's a local data share and global data share, but I very, very rarely see instructions use global data share, so I'm ignoring that part. So what are the issue conditions? They say it's very apparent to see that no 2 instructions can go to one unit in one cycle, because one unit is just have the capability of processing one instruction. So the issue arbiter will decide, say, oh, we'll select at most 5 instructions to go to these 5 units, right? So one instruction, so 5 instructions can go to this 5 unit. That means it can issue 5 instructions at most for every cycle. Okay. It can issue at most 5 instructions in each cycle. There's another condition. If a wavefront is already running an instruction, because this is not something that can complete in one cycle time. It will take like 10 cycles, 20 cycles, or sometimes only 2 cycles to complete the instruction in each pipeline. So it will take some time for the instruction to be executed in these pipelines. So if one wavefront or one warp has an instruction to be executed, if one wavefront has an instruction that is already on a pipeline, we do not schedule another one. Okay, so that is a design that can simplify the GPU architecture design. We'll see why it's designed in this way, what it simplifies in the next few slides. Okay, let's look at the simplest pipeline, the scalar pipeline. The scalar has first a decode unit, which will parse the instructions and prepare and control the rest of the pipeline to stages to do the right thing. We'll see pipeline design when we talk about CPU cores, but here let's just consider there are multiple stages. Then each stage will take one cycle or one or more cycle, but you can simplify it as one cycle to process in each stage. So first we decode, then we read the register, we read the data. When we read the data register, that means we read the register value to the wires. Okay, so there are many, many registers there, right? The scalar register, there are a lot of registers there. There are a lot of registers there. But if you consider a scalar execution unit, that's an ALU, right? We only need 2 wires, 2 operand to feed into this ALU, right? So what do we do? So what's the combinational logic that allows multiple input, one output, and wires one particular input to the output? Yeah, it's the multiplexer, right? So we have a multiplexer here and a multiplexer here, right? So all of them are connecting to both multiplexers. Then we need control logic to select which one can go into the ALU. So here is the multiplexer, and the decode stage is roughly deciding the values on these control wires. Okay. Then the scalar register, ideally we can load it in 1 cycle time, then we execute it in the ALU. We can also assume it only takes 1 cycle. Then we get a result. We actually need to go back to the registers to write a result back. Okay. Then this forms a 6-stage pipeline. It's a fixed stage pipeline. Fetch, right? Issue, decode, load is the load from the register. Then, or sometimes this is read stage, an execute stage, and a write back stage. So this is a 6-stage pipeline. Question? No. This one, the issue. No, issue is the stage that decides which instruction can be executed. Decode is to calculate these values. Okay. Load is to make sure that this data can pop into these wires, into the ALU input wires. Then execute can get a result from here. And write back can go back here. We will revisit this in CPU design, and you will understand the like circuit level design much better in the CPU design. So here, just consider conceptually that there are 6 stages and they're pipelined. So what does it mean by pipelined? In cycle 1, wavefront 1 is here. It's doing fetch, right? In cycle 2, wavefront 1 is doing issue. Assume is selected for issue. Then wavefront 2 is there doing fetching. In cycle 3, we move forward. We get wavefront 1 in the decode stage. Wavefront 2 here, wavefront 3 here. Okay, then it keeps moving until six wavefronts are waiting there, are in the pipeline to be executed. Okay, so this is a pipeline. And in CPU, we typically say a 5-stage pipeline. We'll talk about this later. So there's a minor problem there. So if you consider without that rule, without the rule that say one wavefront can only have 1 instruction in flight, what will happen here? Let's say write back, right? We're writing the result back, but our register still has the old value at this moment. Then we try to load from there. We try to use the data from there. So this will likely to load the old data, not the new data, right? So here, load and write back stage will have this problem. So what is it called? This is called a hazard. A hazard means this pipeline cannot work properly if you don't take action to prevent this from happening. The wrong result can be generated, right? So we need to prevent this hazard to have special mechanism. Now later on, as you can see in the CPU part, we'll introduce many complex approach to solve this problem. But GPU, at least the older style GPU, takes a very simple approach and simply say, we just do not we just prevent this from happening. If a wavefront is already running an instruction, don't issue it, right? Then we'll never have a hazard. Because if we load, it must loading for another instruction, for another verb. Then it's another set of data. So there's we will never have this read after write problem. Right? So it's isolated, totally isolated. No parallelism within one verb. Question? What if we need to we need to use the data that's not calculated yet? So if we follow that rule, no result, no issue. That will never happen, because write back for the same verb, write back always happen at least 1 cycle before issuing. That will never happen. So then the load stage and write back stage must be filled with different verbs. The different verbs, they do not communicate, they're okay. Okay. Okay, another thing, remember the sLoad instruction, the scalar load instruction. We also need to load the data. Then we actually have an extra stage that's called a memory stage. Then the memory stage will connect with the scalar memory. The scalar memory, then it's actually the interface is with L1 scalar cache. Okay, it's a dedicated cache, it's a dedicated in terms it stores scalar information. This case stores instruction information. They store different part of the information. Most likely, this is calculating offset or kernel sizes or addresses. Okay. So scalar memory, it has a scalar L, small scalar L1 cache. Then we talk about here, the vector memory also connect to the vector memory unit, which has an internal pipeline on its own. Then it's also connected with the vector memory unit. Okay. Now the memory bandwidth is much higher here because consider vector memory. When you load the data, right, you're not only loading one piece of data. When you see V45, it's actually 64 pieces of data, right? So it requires much higher bandwidth for vector memory. So we're just giving some preview for the cache part. Scalar memory is shared. Instruction memory is shared all by a group of 4 compute units. Vector memory is dedicated. Okay, so I just simplified. Let's say in the interface that a compute unit needs to connect with 3 memory unit. One is the instruction memory, one is the vector memory, and one is the scalar memory. Okay. Then we're going to talk about the most important part, which is the SIMD pipelines, which is the most important computing power of GPUs. So the VLU instructions calculates instruction starts with a V, that is a vector instruction. Then vector instruction can use scalar register and can also use vector register. By the way, the scalar pipeline only have integer processing capability. There's no floating point calculating capability. So we cannot calculating decimal numbers. Okay, it's always integers. It's mainly designed for calculating addresses, eventually calculate addresses. So the vector memory can load the data, then can be processed by VLUs. VLU contains floating point operations. That's basically the only unit can calculate floating point operations. Okay, then how is implemented internally? In AMD GPUs is implemented in this way. We call this SIMD unit, and it's execute instructions in the SIMD manner. There are 4 SIMD units, and how it works is the wavefront pool matches SIMD unit. So all the wavefront in the wavefront pool 1 can only be executed in SIMD 1. Similarly, all wavefronts from wavefront pool 2 can only be executed in SIMD 2, and so on. Right? It's a one-to-one mapping relationship. So why is designed in this way? Just consider this. In cycle 1, we issue from wavefront pool 1. Okay. In cycle 1, we issue from wavefront 1. Where we can issue to? We can issue to branch scalar vector memory, VLU, LDS, and SIMD1. Okay. I'm just simplifying this. It takes 1 cycle to go here and then 1 cycle to go here. This, you can consider this is basically a decode stage. Okay. In cycle 2, we issue from wavefront pool 2, then we go to SIMD2. Cycle 3, we go from wavefront pool 3 to SIMD3. Cycle 4, we go there. Then in cycle 5, we go back to wavefront pool 1 and issue to SIMD1. It's a round robin process. 1, 2, 3, 4. Okay. So then we need to add some extra rules for the issuing process. So in each cycle, the issue unit will have at most 10 options to select from, right? Because there are 10 wavefront slots in each wavefront pool. We'll have at most 10 options. How many it can issue? It can issue actually 6. There are 5 units, but you also need to consider special instructions like wait count. Wait count doesn't need to be issued. The issuer itself can just decide if it can pass or not. So it's a very simple counter checker. So I would still say the special instruction doesn't really require issuing, but the issuer can issue 5 instructions in one cycle. So basically selecting 5 out of 10 slot, right? It's actually a big ratio, 2-to-1 ratio. And it's not that easy to fulfill the requirement. It's very hard to select all 5 to issue. Then you really have to have 5 different types of instructions. Then all of them, these 5 do not have instruction in the pipeline at that moment. And they have fetched instruction from the instruction memory. All these conditions must satisfy. Then they can issue 5 instructions. For most of the time, they cannot issue 5 of them. They can only issue a small number of them. But if you consider the die size or the resources we allocate to this unit, branch and scalar can be pretty much ignored. They're very, very small. Okay. LDS is large, but there are many programs who doesn't use LDS. Okay. So we only care if an instruction can be issued. If in every cycle, an instruction can be issued to VLU. If it can issue to the VLU, we consider it's successful. Okay. Other parts is not that important. So actually in AMD, there are 2 teams is designing the whole core. One team is responsible for everything other than this part. Okay, I'm not particularly sure about LDS, but at least this whole part is one group. Okay, and this group may have 10, 20 people. Another group is just developing this part. Okay, think about how important this part is. Nobody cares about others. Only if this part is fully utilized, we get really good performance. Everything else is considered overhead. Okay. But to get this part busy, we have to calculate addresses. Okay. Inside SIMDs, what's happening inside SIMD is another level. Think about how many levels we have. GPU level, CU level, and SIMD level. Okay. 3 levels of indentation. And we just really simplified other units, SBSL and VM, and we consider SIMD1, what's inside SIMD1. Then in SIMD1, we have ALU pipelines. Then just consider these pipelines as the necessary steps that we need to calculate some operations. For example, multiplication, right? Multiplication may require multiple steps to execute. Then may take sometimes a multiplication may take 6 cycles, 8 cycles. Some division may take 12 cycles, 20 cycles. Just consider sine, cosine, log operations that can take a very, very long time. So these are lengths. Okay. Just consider multiplication. Okay. Simplify multiplication. Assuming a multiplication takes 8 cycles to complete. Then this lane can process 1 thread level instruction. What is thread level instruction? Then what's the other side of thread level instruction? It's warp level instruction or wavefront level instruction, right? So when you say how many instructions that a GPU can execute in one cycle, you have to say, are you talking about warp level instruction or thread level instruction, right? So here we're talking about thread level instruction. Each lane can process 1 thread in one cycle, okay? Now we just fill in this pipeline, then can execute. We have more demo later. Then in one SIMD ALU, there are 16 lanes for single precision floating point numbers. 16 lanes. Okay, start to consider this as a swimming pool. It's a swimming pool. There are 16 lanes. Okay, then the length is decided by number of stages. And it takes some time for a swimmer to swim from there to there. Okay, and consider wavefront is going this way, right? All the swimmers are swimming at the same speed. So there's a wavefront that's deciding where they are. Okay, let's play this process. In cycle 0, wavefront 0. Sorry, in cycle 0, wavefront 1 got issued. So assuming one instruction being issued to SIMD. Let's also simplify the issue stage and the VLU stage. Okay, just in cycle 0, one instruction of wavefront pool from wavefront pool 1 got injected into these lanes. Then we start to execute. In cycle 1, wavefront 1, quarter 1. I call it quarter 1. Why? Because in AMD GPU, every warp is 64 threads, right? 64 threads. Then there are 16 lanes. That means we can only execute a quarter of a warp. There's 16 threads. So cycle 1, what we'll do is we'll calculate this stage for the first quarter of this wavefront, of this warp. At this stage, wavefront pool 2 is issuing to SIMD2. Okay, this happens at the same time. Keep going. In wavefront pool, in cycle 2, everything moved down one level. So quarter 1 is executed in the second stage. First stage is processing quarter 2. Okay. At this moment, wavefront pool 3 is issuing to SIMD3. Now keep going. Wavefront pool 4 is issuing to SIMD4, and we have Q3 executing the first stage. Then move to cycle 4. We have all the quarters in the pipeline. Then it gets the wavefront pool 1 to get execution, right? To get issued. So the issuer will issue from wavefront pool 1. Then at this stage, in the next stage, we have wavefront pool 2 and quarter 1 there. Okay. So then in cycle 6, then we keep going down, right? So it's not a coincidence why we have 4 SIMDs. We have 4 SIMDs because the warp size is 64 and we have 16 lanes in each SIMD. In this design, if everything works smoothly, we can fill the whole pipeline without any bubbles. So in theory, we can get a maximum performance. Okay. Careful is a very careful design of the SIMD system. So in AMD, something I learned from their process is how these different modules or different blocks, say one group is working on this part, another group is working on this part. There must be a manager, a leader, or architects who design what's the throughput and what's the required value. Say, I want this throughput to be, say, 16 instructions going out from SIMD, right? Then this part say, oh, I'm going to take one instruction per every 4 cycles. And once they start to have this contract, then they start to design on their own. Then the manager or the architect's level, what they are doing is basically they consider something like, oh, I want this GPU, I want it to be able to render 4K video, for example. This is targeting high-end games for 4K video. They can just calculate how many pixels they need to calculate per cycle. Then they need to know how many pixels, how many vertices they need to calculate per cycle. Then they just go backward and start to calculate every stage that, oh, I want this thing to output 16 values per cycle. Okay. Then they also need to calculate this, assuming that, or for every compute task, then we have, for every compute task, we need to load this part of memory, this amount of memory. So say for every compute, we need to load 4 bytes of memory. Then we need to design the vector memory with that particular bandwidth. Then the architect or the manager will start to give the L1 cache group a task. Say, I can give you 3 volt, I can give you 3 millimeter square die size. You have to fulfill this requirement for me. Although it requires back and forth negotiation, probably it's just theoretically impossible, but that's how a manager in AMD designs such a system. From the requirement, say I'm going to, this is a high-end, the high-end need to support 4K gaming, then they just calculate everything backwards. Then they just match the requirement. The biggest failure of a design team is you have one part that is super powerful, the other part cannot catch up. Right? They say your SIMD unit are super powerful, but your memory is super slow. It's wasteful, right? You have large die size, you have high cost, but eventually you can only render 1080p games. Okay, so perfect matching and keep every part of the circuit busy is the art of design of computer architecture. Okay, I'm not going to play the animation for the rest of the cycles. They should consider they can just go through this pipeline. Okay, so just one concept here, latency and throughput. Latency and throughput are not necessarily directly related. For example, we can have a very, very long latency, a very deep pipeline here. So it will take, say, 100 cycles to calculate results. We can still achieve a 1 cycle per 16 instruction, per 16 thread level instruction per cycle throughput, a very high throughput, right? So in theory, especially for compute-oriented GPU, is optimized for throughput, not for latency. So we can allow longer time to access, say, memory. GPUs do have longer access, require longer time to access memory compared to CPU. But because there are so many other threads waiting there, GPU can deliver much higher throughput than CPUs. Or in other words, GPUs are optimized for throughput. CPUs are optimized for latency. Because you type a key on keyboard, it has to respond, has to show the character on screen as soon as possible. For GPU, you typically, especially for general purpose GPU, you typically do not need to consider the latency requirement. But for gaming GPU, you do need to consider some sort of latency. It cannot be too slow. Okay. So I think that goes to some calculation. Okay, before we do some calculation, what we can do is, let me introduce some of other GPU design. This is how AMD designs their GPU. Then this is the GCN architecture, the older GCN architecture, graphics core next. It's already their second biggest big generation of AMD GPUs. And later on, they have this architecture called RDNA architecture. Then they also have this CDNA architecture. Okay, so after GCN retired, then they start to develop new architectures. What's their new architecture is called RDNA architecture. But they also have the CDN architecture because they start to branch for 2 product lines. This CDNA stands for compute, R stands for Radeon, but it's basically for graphics, for gaming. Okay, so it's not a coincidence that I write GCN together with CDNA because they are basically the same architecture, just newer. Okay, so CDNA did not start from scratch or did not change that much. RDNA changed a lot, super a lot. CDNA is basically an evolution, like a minor change of the GCN architecture. Then also, RDNA actually have a similar architecture with NVIDIA. NVIDIA architecture, they're similar. Okay, so let's write this. Let's do some comparison. GCN, CDNA, then RDNA, NVIDIA. Okay, so first thing is warp size. You write smaller. GCN, CDNA. The first thing is warp. size. GCN CDN has warp size of 64 thread, and RDNA and NVIDIA has 32 thread. Okay, quick question. What's the advantage of these two designs? 64 thread versus 32 thread. Yeah. Yeah. In summarize, there are several things. So 64 threads in theory have higher computing throughput. And because you issue one instruction, you can get more calculation done. So throughput efficiency is higher. But the problem with 64 thread is not that friendly in terms of control flow, right? So in terms of control flow, when there's thread divergence, then the efficiency can be even lower. Efficiency can be even lower because only a small part of the warp is executing. Just look at here. If you only have one thread is executing something, all these 4 quarters needs to go through this pipeline. Just no stop. We have to feed them through the pipeline. Even if there are some ways that we can turn off some calculation, the time is wasted, right? So it will take 4 cycles, 4 stages in the pipeline. So another thing is when we issue memory instructions, issue memory transactions to send to the vector memory, this requires more data. This requires fewer amount of data. Okay, so these, in ideal case, these have higher throughput. 32 thread is more friendly to 32 thread is more friendly to latency sensitive cases, so more friendly to graphics. That's why RDNA choose the new number. CDNA stays at an old number. Okay. Second thing, SIMD length. So for SIMD length, this has 16. This has 32 per SIMD. Okay. 16, that means 4 cycles per warp. 32 and 32 means 1 cycle per warp. Okay. So still, you see, there are more resources here, right? So it's hard to say which one has higher throughput. It's just different ways of scheduling. But definitely on this side, it's more latency friendly. That means for calculating one warp, it's just 1 cycle thing. This requires 4 cycles. Okay. Then issuer or issue unit. There's 1 issue unit per CU. There are 4 per CU. Okay. So why 4? Because you have to issue to every SIMD unit in every cycle. Right? Because you don't have this 4 cycle thing. In this case, every 4 cycle is issued to each SIMD unit. Every 4 cycle is issued to the same SIMD unit. Here, you have to issue every cycle to every SIMD unit. So for every SIMD unit, you have to have an issuer on its own so that you can keep the SIMD unit busy because it only takes 1 cycle to calculate that warp. Okay, so you can see they're very different. They have very different designs. And here we basically say wavefront pools and SIMD unit. In RDNA, especially in NVIDIA, we typically call it subcores. What is a subcore? Subcore is basically like this: a wavefront pool, a issuer, then a SIMD unit. This is a subcore. Then there are 4 subcores in one SM. Okay. There are 4 subcores. So a wavefront pool, just consider one wavefront pool, one issuer, and this issuer is dedicated to this wavefront pool and to this SIMD unit. Okay. Then there are 4 subcores in each SM. This is the RDNA and NVIDIA core design. Very similar here. You can also say a wavefront pool and the SIMD unit is a subcore. It's just they share one issuer. Okay. Any questions? Okay. So just give you some example of some other designs of GPUs. Then they have different considerations. Then one quick thing. So if you consider the number of SIMDs are always 4, right? Number of SIMDs per CU. Here is 4, here is also 4. But you consider the number of lanes. This is 16 lane, this is 32 lane. So that means lanes per CU. Here is 64, here is 128, right? Just a multiplication. Then because of this, one NVIDIA SM is more powerful than one AMD CU. Okay, it's almost double the amount of calculation capability. And it's actually very interesting that when RDNA comes out, what they name it not CU, they just name it as DCU, dual CU. That means it's combining 2 CUs together. It has the power of 2 CUs, 2 compute units. Okay. Okay. Question? Mm. Yeah, we're executing from pool 1. So we're issuing wavefront 2 in the previous cycle. Yeah, we're issuing wavefront 2 here. Oh, I'm just saying, at this time, at cycle 3, wavefront pool 4 is issuing into wavefront into SIMD4. Okay, so there's always a one-to-one mapping. At this moment, previously, we're only looking at one SIMD. but just imagine something similar is also happening in other SIMDs. Yes, we want to keep all the SIMDs busy, right? So at this cycle, it's similar to this cycle, right? Cycle 1 is similar to cycle 0 for wavefront pool 2 and SIMD2. Okay, no, it's just hard to understand. Let's draw this. I cannot really draw 4 SIMDs. They're symmetrical. Let me think. I don't have to draw a swimming pool there. So this is SIMD1, SIMD2, SIMD3, and SIMD4. Okay, so in cycle 0, what happens is wavefront 0, wavefront 1 is issued here. Okay, what happens in cycle 1? I have to show you in animation. Okay, so stage 1, this is wavefront 1, quarter 1. Then cycle 1, we have wavefront 2 here is being issued to there. Okay, cycle 2, this moved down. And this is executing wavefront 2, Q1. Now we're issuing wavefront 3 here. Okay, then cycle 3, keep going. W4, 1, W1, Q1, Q3, 2, Q2, W2, Q1 here. Then W3, Q1 here. Okay, just since I draw this one, let me just draw one more stage. And I think I'm good. Q1, Q2, Q3, Q4. W2, Q1, 2, 3. W3, Q1, 2. W4, Q1. Then also we're issuing W5 to here. Right, so this requires an animation, it requires a video. Okay, so all of them are busy. So you see this perfect design, so this issuing is going cycle by cycle, round robin issuing, and it exactly takes 4 cycles for the first slot becomes available. So it's a perfect rotating machine. Okay. Okay. Now, at the end, let's do some calculation. So how many threads that the GPU runs concurrently? So where we're looking for this question, we're mainly looking for wavefront pool 4. Sorry, wavefront pools, 4 wavefront pools. So we use R9 Nano, for example. Why we use this one? It's just because it's super easy to calculate. Okay, it's a very old 2015 small form factor GPU, but it's actually a high-end GPU, very powerful. It's just, you will realize how easy to calculate. Everything is in powerful tools or thousands gigabytes, something like that. Okay, how many threads that the GPU runs concurrently? We need to look at wavefront pool. So there are 10 wavefront per wavefront slot. Then 4 wavefront pool per CU. That means 40 wavefront per CU. That's something we already calculated. And 64 work item or thread. Work item is AMD terminology for thread. I never introduced that. I'm keep switching between AMD terminology and NVIDIA terminology. Let's just do a quick summarize. Okay, AMD terminology, NVIDIA terminology. AMD and NVIDIA. AMD call this thing called work group. I really don't like this name. It's okay. We never introduced this one. On NVIDIA side, this thing is called block. So I have always been using block, right? Or sometimes you may call it like cooperative thread blocks. It's okay. Let's just call it block. Then in AMD, we have something called wavefront. I like this name because it means something, or sometimes it can be as shorted as wave. Okay. Then in NVIDIA, this is called warp. Okay, it's also very commonly used. Then at the lowest level, this thing is called work item. And this side is called thread. And so basically, other than wavefront, I pretty much use NVIDIA terminology. And another thing, this is called CU, compute unit. This side is called streaming multiprocessor. AMD calls the data as LDS, local data share. NVIDIA calls this thing shared memory. Okay, some term mapping. Let's come back here. So 64 threads per wavefront. That's CDNA or GCN architecture. So then we can calculate 2,560 threads per CU. By the way, I forgot one thing. Have you heard of the terminology called CUDA core? CUDA core. Then NVIDIA just advertise their GPU, say how many CUDA cores in this GPU have. And typically it's several thousand. So what is a CUDA core? CUDA core, now I would say the matching term is lane, but lane is not rather official AMD terminology. AMD just doesn't have this thing, have a matching term. But I would just put lane here. So remember, how many lanes are there? Like 64 lane per CU, right? Then this on this side, they just call 128 CUDA cores per SM. Per CU, 16 or 64 lanes per CU, 16 lanes per SIMD. Okay. 2,560 thread per CU. That's a large number. Think about CPU. Then even the highest end cannot run this number of threads at the same time. Okay. Then keep going. 64 CUs per GPU. That's 16. That's 160K threads per GPU. Okay, so that's a huge number, right? So many threads that are executing at the same time, waiting there to be executed. That's one question. Another question is, how many instructions a GPU can complete per cycle? Is it the same number? Why is not the same number? That's right. So this number of threads per GPU means the number of threads that are currently executing. That means can executing around the same time. They are waiting in the wavefront slot to be scheduled, but not all of them can be scheduled in every cycle. Now, in theory, in each cycle, only 1 out of 10 can be selected. But actually, 1 out of 40 can be selected. So what we look at is the number of lanes in the SIMD. So assuming all the lanes are fully occupied and it's a perfect pipeline. In this case, we can say 16 lanes per SIMD, right? Then 4 SIMD per CU, that's 64 instruction per CU per cycle. Then here instruction is thread level instruction. And keep going, 64 CUs. And that's why I really like R9 Nano, it's always 64. So multiply by these three numbers together, 16 by 4 by 64, we get 4 kilo instructions per GPU per cycle, right? So in every cycle, we can complete 4 kilo instructions. And here there's something that is hidden. We only consider VLU instructions, right? Nobody cares about the other parts. Only VLU matters. Other parts are overhead. We only care about if VLU are fully utilized or not. Okay, 4 kilo instructions per cycle. Then next question. How many floating point operations a GPU can complete per cycle? My mistake, it should be per second. That's something I want to say. So how to calculate this one? We need to know how to convert cycle to second, right? That's the most amazing thing of R9 Nano. It runs exactly at 1 gigahertz. It's just super easy to calculate. So if it's 1 gigahertz, how long is a cycle? It's 1 nanosecond, right? Exactly 1 nanosecond per cycle. So it runs at 10 to the power of 9 cycles per second. So I multiply these two numbers together, we get 4E12. Right? Because here is E9, here is E3, right? 10 to the power 3, and here is 10 to the power 9. And basically, we want to convert it to 4.096. That is E12 operations per cycle. Question? A lane is not a register. A lane is a combination logic. You can simplify it's a combination logic. At least one lane stage is a combination logic. Okay. So yeah, so it doesn't store anything. It just can process, say, two floating point number multiplied together, right? Yeah, but it takes a few cycles. That means there are registers in between. Between every stage, there must be registers to lock the data up, right? But the goal of a lane is not storing data. Okay, so this is the number we get, or if we convert it, that's 4 teraflops, right? 4.1 teraflops. But there's a problem. I look at the specs. This is from Tech Power Up. What they say? We're calculating a single precision floating point number. It's 8.192 teraflops. It's exactly 2 times the value we calculated. What's the problem? Okay, I can tell you. There are special instructions called MAC operation or MAD operation. What's MAC? MAC is multiply and accumulate. MAD is multiply and add. So you may have three operands. The first two operands multiply together and add a third value. This is super useful in matrix multiplication because in matrix multiplication, it's an accumulating process. Right? You multiply two numbers together and accumulate it to the value, the output value of that cell. And keep accumulating until you calculate the whole row, column and whole row multiplication. Then you get the final result. That's matrix multiplication. It's super useful for matrix multiplication. That counts as two floating point operations per instruction. That's eventually we get this number. Okay. So the power of R9 Nano GPU is 8.19 teraflops per second. PS, flop PS. So then a question. What's the actual value that we can get? So I can basically tell you, if I write a matrix multiplication, if you give me 5 minutes to write a matrix multiplication, assuming it's bug-free, assuming you can get the correct result, my estimation is about 1% of the utilization. Okay. Then if NVIDIA or AMD, they have a whole engineering team, write their own libraries, they can get 50% of utilization. If everything is perfect, square matrices, and the second matrix is transposed, and transposed is just more friendly for memory access. We can talk about that in the next lecture. The first one is regular. The second one is transposed. Both of them are square, so perfect cases. The highest value I tested on AMD GPU is about 80% of utilization. So for a program that achieving 80% of utilization, in my mind, that's the maximum that you can actually achieve. That's the perfect situation. The most professional team working for the longest time on the most popular program, matrix multiplication, they can get 80% of utilization. So I would say 80% utilization is the maximum that a typical program can achieve. Okay, so this is how we calculate this whole process, right? How calculate the processing power. Still 8 teraflops from old standard is very fast. From a current standard, it's rather slow. So it's developed by a lot. It's already 10 years, released for more than 10 years. It's a really old card. Today, I would say 2 times, 3 times is rather normal. Now with tensor cores, it can be 10 times faster than this, more than 10 times faster than this. We'll talk about tensor cores later. But here, this is what they can achieve at this level. Okay, so in the second half of the semester, we're definitely going to talk about how tensor cores works. But that's I would say that's even not a part of the GPU. It's something like a TPU or NPU, that type of architecture.